Good morning to all. We are going to discuss electrostatics. Already in the previous sessions, we had discussions related to the electric fields, electric potentials, Gauss's law applications, and then we started with the capacitors. In the previous session, you fellows were given explanation related to the effects of dielectric introduced between the plates of a parallel plate capacitor without a battery. Now we have to discuss about the effects of the same dielectric introduced in the region between the plates of a parallel plate capacitor with the battery. Let us now discuss about the fundamentals what you had in your previous session. And the plates of a parallel plate capacitor are connected to a battery. Then the plates are charged like this. Equal number of charges will be there on the plates. If there are 6 positive charges, then there should be 6 negative charges on the other plate. Now the battery is removed and you are introducing a dielectric in the region between the plates of a parallel plate capacitor, which is to have a dielectric constant epsilon r. Initially, the electric field in the region between the plates is E naught. The separation between the plates is D. Initially, before the introduction of dielectric, the electric field is E naught. As you know very well, the electric field is E naught, potential is V naught. Then the charge is Q naught, potential energy stored is taken to be U naught, and then there is another physical quantity, the capacitance of the capacitor, which is taken as C naught. These are all the values of the different physical quantities before the introduction of dielectric. When the dielectric is introduced in the region between the plates of the parallel plate capacitor, the electric field changes to E equals E naught divided by epsilon r. You had this discussion already in the previous session. E equals E naught by epsilon r. Potential V equals E into D, where E is E naught divided by epsilon r into D. So this will be E naught D by epsilon r. So I can write V naught divided by epsilon r. So potential also decreases by epsilon r times. Since the battery is disconnected, the charges given to the plates of the parallel plate capacitor remains unchanged because there is no external agency to push the charges onto the plates of the parallel plate capacitor. So the charge will be the same as Q naught. Then the capacitance of the parallel plate capacitor with the dielectric is C equals we can write Q divided by V, where Q is Q naught, the same charge, and V is V naught divided by epsilon r. So I can write Q naught by V naught is C naught. Epsilon r goes to the numerator, so epsilon r C naught. So the capacitance increases by epsilon r times. And then when you speak about potential energy, U equals half. Since the charge is constant, I can write Q square divided by C. As the charge is Q naught itself, I can write half Q naught square divided by capacitance of the capacitor is epsilon r C naught. So Q naught square divided by C naught, and this 2 will exist. So the potential energy initially is U naught, and that is divided by epsilon r. So I can say potential energy decreases by epsilon r times. Along with the potential energy, we can also speak about energy density. The energy density can be calculated like this. Energy density in a capacitor with air medium or vacuum. This is given by half epsilon naught E square. The same energy density in a capacitor with a medium, say dielectric, is half epsilon naught or epsilon E square, which is half epsilon naught epsilon r E square. As the initial electric field without the introduction of dielectric is E naught, I can write this as half epsilon naught E naught square. As the electric field changes when you introduce a dielectric, I can write this as half epsilon naught E square, half epsilon naught epsilon r E square. Now, this can be manipulated like this. This is small letter u. What is the difference between electric potential energy and potential energy density? Energy density is energy per unit volume. So, it is represented by small letter u. U equals half epsilon naught epsilon r E square. I can write this as u equals half epsilon naught epsilon r. Instead of E, electric field changes as E naught divided by epsilon r. So, E naught square divided by epsilon r square. Epsilon r gets cancels out. We will have half epsilon naught E naught square divided by epsilon r. Half epsilon naught E naught square is nothing but small u naught divided by epsilon r. This is small u. So, I can say energy density decreases by epsilon r times. Energy density decreases by epsilon r times. In the same way, see, we discussed nearly 6 physical quantities which are associated to the capacitors. So, electric field intensity decreases by epsilon r times, potential decreases by epsilon r times, charge remains same, potential energy decreases by epsilon r times, capacitance increases by epsilon r times, energy density decreases by epsilon r times. Now, we are going to discuss about the other idea that when a capacitor is introduced with a dielectric, with the battery remains connected. These are all the results what we obtained for a battery disconnected between the plates of a parallel plate capacitor. Now we are going to discuss about the effects of dielectric when a battery is connected across the plates of the parallel plate capacitor. We shall see one by one. We shall now start with the effects of dielectric with the battery connected. With the battery connected. Let us say a parallel plate capacitor is connected with a battery. The plates are charged as positive and negative. As I mentioned, equal number of positive and negative charges will be produced. Correspondingly, electric field lines will be acting from positive to negative charges. The field, electric field can be represented as E naught in the region between the plates. Now, the battery of potential V is connected here. The battery is connected as it is. It has not been removed from the plates of the parallel plate capacitor. Now, if a dielectric is introduced between the plates of a parallel plate capacitor, whether the battery remain connected, what will happen? The electric field in the region between the plates decreases with the dielectric. Dielectric is there now. With the dielectric is there. Dielectric constant is epsilon r. Separation between the plates is d. Here also separation is d. Now the electric field decreases, but the battery remains connected, which means the potential difference across the plates of a parallel plate capacitor remains constant. If potential difference remains constant, if V is equal to V naught, as the battery remain connected, then the electric field should also remain the same. Reason is very simple, V equals E into D. V equals E into D. As the potential is V naught, V equals V naught, potential remain constant. The electric field also should remain constant. So in order to bring out the electric field a constant, the charges are supplied by the battery to the plates of the parallel plate capacitor in order to increase the electric field. So what will happen is that the charges on the plates of a parallel plate capacitor increases so that it will bring back the electric field to its original value. So the original electric field will be brought out. E has become E naught. E has become E naught. What has happened here? Potential is still remaining constant. V equals V naught. What happened to the electric field? Electric field is also constant, E naught. But what happened to the charge? It is not the same. Charge got increased over the plates of the parallel plate capacitor. This was first observed by Faraday. And the charge over the plates of the parallel plate capacitor increases by epsilon r times. As you know very well, the electric field in the region between the plates is E naught without the introduction of dielectric. Potential is V naught, charge is Q naught, capacitance is C naught, potential energy is U naught, potential energy density is small u naught. Here I am saying the charge Q now with the introduction of dielectric, the charge Q is epsilon r times Q naught. So charge increases by epsilon r times. What will happen to the capacitance of a parallel plate capacitor? C equals epsilon naught or C naught equals epsilon naught A divided by D. C equals epsilon A divided by D. And we can write here in this particular case, capacitance of a capacitor C equals Q divided by V when with the introduction of dielectric. With the introduction of dielectric, C equals Q divided by V. What happened to the charge here? It has increased by epsilon r times Q naught. What is the value of potential? V equals V naught. What is Q naught by V naught? I can write C naught is equal to Q naught divided by V naught. As C naught equals Q naught divided by V naught, I can write C equals epsilon r times C naught. C equals epsilon r times C naught. So the capacitance of the capacitor increases by epsilon r times. Simply we can say capacitance of a capacitor can be represented as C equals Q divided by V. Q divided by V. As the potential remains constant, the capacitance of the capacitor increases with increase in charge. As I mentioned earlier, the charge increases by epsilon r times, so the capacitance also increases by epsilon r times. C equals epsilon r C naught. The capacitance of a parallel plate capacitor increases by epsilon r times. There, in the earlier case, without battery, a dielectric introduced between the region between the plates of a parallel plate capacitor without a battery, the capacitance increased there also. C equals epsilon r C naught. But the reason for the increase in the capacitance is quite different between these two cases. There, it is due to the change in potential, here it is due to the change in charge. So C equals epsilon r C naught. Capacitance increases by epsilon r times. And then, what about the potential energy? Potential energy can be given as U equals. Actually, if I am representing U, that means I am speaking about the potential energy stored in the parallel plate capacitor introduced with the dielectric. U equals half C V naught square. Why am I introducing this expression? Why shall not we use U equals half? Why shall not we use U equals half Q naught square divided by C naught? Why am I not using this expression? Reason is very simple. If you consider this expression, there is a change in the charge as well as there is a change in the capacitance. So that will not give you the exact change produced in the potential energy. So in order to study about the potential energy, you have to consider the expressions which explains about any of the physical quantity which is coming as a constant. When battery is disconnected, there the charge is constant, so you used U naught equals half Q naught square divided by C naught. When the battery is connected, then here the potential remains constant. Potential remains constant. So I am taking the expression U equals half CV naught square. U naught, the initial potential energy, U naught is equal to half C naught V naught square. The potential energy with dielectric is U equals half C V naught square, half C V naught square. Now we can say what will be the change that is produced, or we can see what is the change produced in U. U equals half C is epsilon r C naught into V naught square, since C equals epsilon r C naught. C naught V naught square into half is nothing but U naught. So U equals epsilon r times U naught. U equals epsilon r times U naught. So the potential energy also increases by epsilon r times. Once again, as we discussed earlier, potential across the plates of a parallel plate capacitor is constant because the battery remains connected. So the electric field in the region between the plates of the parallel plate capacitor is also a constant. So we can conclude, if the battery is still connected and a dielectric is introduced in the region between the plates of a parallel plate capacitor, then the potential remains constant, electric field between the plates of the parallel plate capacitor remains constant, charge increases by epsilon r times, capacitance increases by epsilon r times, potential energy increases by epsilon r times. Now we can see the energy density also. Energy density, as I mentioned earlier, is represented by small letter u. Small letter u. Once again I am telling you, the potential energy means energy density stored in the plates of a parallel plate capacitor, in the region between the plates of a parallel plate capacitor, is given by the expression small u naught is equal to half epsilon naught E naught square. As I mentioned earlier, U naught is the energy density before the introduction of dielectric. E naught is the corresponding electric field in the region between the plates. Now, if a medium is introduced, the energy density is represented as U equals half epsilon E square. Half epsilon E square. Now, in this particular case, the capacitor plates which are connected with the battery and the dielectric is introduced between the plates. We can say the electric field remains constant. So, small letter u is equal to half, epsilon can be taken as epsilon naught epsilon r, E is equal to E naught. So, E naught square. Since epsilon equals epsilon naught epsilon r, E equals E naught. So, what will happen? Half epsilon naught E naught square, half epsilon naught E naught square is U naught. So, small u equals epsilon r times U naught. Small u equals epsilon r times U naught. So, energy density also increases by epsilon r times. So, if potential energy increases by epsilon r times, then energy density also increases by epsilon r times. So, finally, we can compare all these changes produced in all these physical quantities when dielectric is introduced between the plates of a parallel plate capacitor without battery and with battery, so that you can check it easily. We will now compare the changes produced in various physical quantities when the capacitor plates are introduced with the dielectric, the region between the plates of the parallel plate capacitor is introduced with the dielectric, without battery and with the battery. So, the various physical quantities what we are going to deal with is charge, potential, electric field, then capacitance of a capacitor, C, energy is capital U, then energy density, small letter u. Then what happens if the dielectric is introduced between the plates without battery, and then with the battery? Without battery, charge remains same, potential decreases by epsilon r times, electric field decreases by epsilon r times, capacitance increases by epsilon r times, energy, as you know, U equals half Q square divided by C. Charge remains same, capacitance increases by epsilon r times, so energy decreases by epsilon r times. Decreases by epsilon r times. Energy density also decreases by epsilon r times. Now, with the battery, what will happen to the charge? Charge increases by epsilon r times, potential remains same, electric field remains same, capacitance increases by epsilon r times, energy you can say increases by epsilon r times, then energy density also increases by epsilon r times. So, this is the conclusion. So, if you are very clear with these ideas, you can easily attend all the questions related to the effects of dielectric without battery and with battery. Now, we shall go on to the next heading, combinations of capacitors, series and parallel combination of capacitors.